We collected a good amount of data, more than 100 observations. We know its trajectory fairly well. We know it came from outside the solar system.
On July 1st, 2025, astronomers confirmed the third known interstellar visitor racing through our solar system, an object catalogued as 3I Atlas. Within days, its speed, brightness, and near straight-line path defied the models that normally tame wayward comets. Faced with contradictions, researchers poured every observation into a cutting-edge quantum AI and asked it to simulate everything the data allowed. The output did not challenge assumptions alone. It squeezed the odds that Atlas is natural to a sliver and raised questions. What kind of visitor follows a path that looks planned, and why now? Discovery, numbers, and the leak of unease. Atlas began as a whisper in a crowded sky. A survey array in Chile flagged a dim point sliding across Serpens Corda, and within hours observatories from Hawaii to La Palma were feeding astrometric fixes to the minor planet's center. Initial solutions would not behave. The orbit was hyperbolic, with an eccentricity beyond 6, which meant the sun could barely bend it. The speed held near 58 kilometers per second, fast enough to cross the Earth-Moon gap in 2 hours. And yet its light curve was brighter than a cold, far comet should be. Pre-discovery frames from Zwicky and Pan stars tightened the math and erased the hope that this was a trick of noise. 3I Atlas was interstellar and already shedding a soft coma at 4.5 astronomical units, where most newcomers are still inert. The approach angle added to the unease. Instead of diving from a random orientation, Atlas threaded into the ecliptic within a few degrees, a lane usually reserved for bodies born here. Then the geometry sharpened. Projections showed passes that would carry Atlas inside comfortable ranges of Mars, then Venus, then Jupiter, each within weeks of favorable orbital positions. No one called it targeted, but everyone noticed how clean the sequence looked, like a survey scheduled long ago. On August 12th, the James Webb Space Telescope measured a carbon dioxide to water ratio near 8:1. Inner system comets rarely give carbon dioxide the lead, and when they do, the release usually swells in smooth ramps driven by heating. Atlas pulsed, gas spiked, fell to baseline, and spiked again with a cadence tied to a rotation period of about 16.8 hours, as if specific surface sectors woke when they faced the sun and slept when they turned away. Comparisons to known families failed. Nanometer-scale dust grains dominated the outflow instead of the broader mix expected from friable ice. Trace molecules like carbonyl sulfide appeared in proportions at the edges of known classes. By the third week, 2 questions had crystallized. Why is this object so bright, fast, and well-placed? And why does its chemistry behave like a valve rather than a thawing snowball? Ordinary models balked. Dynamical integrators that digest millions of steps wandered into divergent futures when they tried to fold in the pulses, and non-gravitational forces could not explain the geometry without fine-tuning. That was when the conversation turned from bigger clusters to a different kind of computation.
Billions of objects in a database, and that'll be available for the whole world to use, for scientists, and even the public will be able to go in and download all those images.
If the parameter space would not be corralled path by path, perhaps the only way to see it whole was to explore many plausible paths at once. Quantum simulation moved from theory note to plan, not because it sounded fashionable, but because nothing else promised to keep the contradictions in a single frame. Could a machine that holds many futures in superposition tell us which futures are possible? Why quantum, how it was built, and what it meant to ask. Classical pipelines power almost every orbital solution used in astronomy. They take a path, slice it into many small steps, and march forward while adjusting for gravity, radiation pressure, and outgassing. With 3I Atlas, that approach fell apart. Each time analysts added the pulsed emissions or allowed for the tiny thrust such pulses could create, the solution space split into a forest of possibilities. Supercomputers could chase a branch, but every new assumption spawned more branches, and the answers wandered instead of converging. Engineers at NASA's Quantum Artificial Intelligence Laboratory proposed a pivot. Rather than drive one future to completion and then start over with a slight variation, run all the important futures simultaneously and let probability decide which survive the data. In practice, that meant building a hybrid workflow. Classical code cleaned and normalized the incoming observations, and a bank of graphics processors emulated quantum circuits that could hold many states in superposition before measurement. A CUDA cluster of H100 devices became a scientific instrument that could map likelihoods across a wide field of uncertain parameters. The team encoded orbital elements, non-gravitational coefficients, and spectral priors as quantum states. Entanglement-linked variables that observations suggested were coupled, such as rotation phase and emission bursts. Every run effectively unrolled a multiverse of Atlas histories. Measured against new telescope reports, the superposition collapsed, removing futures that no longer fit and reinforcing those that did. They highlighted which families of explanations matched everything measured so far. Scenarios that once dominated, such as a large natural comet driven by water and dust, shrank to thin streaks along the margins. Hypotheses that had sounded eccentric, such as timed venting used for attitude control, swelled into high likelihood ridges. The simulation was not declaring an origin. It was ranking explanations by how well they matched the stream of observations. Within a week, the ranking became hard to ignore. Natural drift sat under 5%. Derelict object with inert structure sat near 40. Active modulation with momentum trim through timed venting rose above 50. To keep the model grounded, the team imposed priors from laboratory sublimation curves and past interstellar visitors, then allowed the quantum layer to relax them only when new data insisted, while cross-validation verified stability and sensitivity tests exposed which inputs steered results. A map analysts could probe. If guidance is the simplest fit, what observable should move next, and can we catch it in time to tell the difference? Chemistry, pulses, and the case for controlled shedding. The early spectra felt upside down. Carbon dioxide dominated while water lagged at roughly 8-to-1 by mass, and release came in disciplined bursts, rather than the soft ramps taught by thermal models. Webb's measurements and ground-based detections confirmed a rotation near 16.8 hours and tied the brightest emission to repeating longitudes that lit when facing the sun and dimmed when they turned away. Layered ices can step releases, yet the regular cadence pressed a harder option. If vents act like valves, outflow can be timed for momentum as well as chemistry. Laboratories calculated thrust from carbon dioxide jets at the measured rates. It would not move an object into a new orbit in a day, but over weeks it could trim a path by fractions of a percent, the difference between a wide miss and a close survey pass. Submicron dust sizes explained some of the brightness without requiring impossible diameters, but composition kept needling assumptions. Carbonyl sulfide and carbon monoxide rode in unusual ratios, and nickel lines appeared without a matching iron signal. Nature rarely splits that pair, while engineering often favors nickel in high-temperature alloys. Rather than leap to hardware, the team asked how sorting could occur. Sublimation thresholds and electrostatic lofting can bias grains, but the quantum ranking resisted those escapes. Runs that relied only on sorting produced tail chemistry too far from the spectra. Runs that allowed a small reservoir enriched in nickel, whether by accident or intent, fit better. The A did not know what a nozzle is, but it ranked flow behaviors, and it kept rewarding scenarios in which the same surface sectors turned on and off cleanly with the spin, concentrated the jet, and shed just enough mass to shape the path. Overlaying emission times with tiny kinks in the trajectory deepened the concern. High-precision astrometry recorded subarcs, second bends that followed brightening bursts, and the explanation that venting both cooled and steered moved from speculation to the leading ridge on the map. Catalogued comets do strange things, but strange usually looks chaotic, with tumbling, ragged flares, and irregular periods. Atlas behaved methodically. It kept its spin, repeated its brightening, and drifted in the very direction a navigator would choose to maintain a near-ecliptic survey track while conserving mass. Methodical behavior invites a hard question. Is there an internal controller, a passive geometry that behaves like one, or a now silent architecture whose residual features still mimic guidance? Each alternative left a different fingerprint on the next week of light curves, and by September one conclusion was unavoidable. If the pulses are natural, they work in a way that helps Atlas stay on a path that looks chosen, and if they are not, the object is not just visiting, it is navigating. Could a relic carry habits from its makers without being alive in any sense we understand? A path that threads the planets, and the math that refuses chance. Trajectory analysts at the Jet Propulsion Laboratory ran integrations the moment a long arc of observations locked the orbit. The result looked like a dare to statistical comfort. After slicing through the inner system on a retrograde track that stayed within a few degrees of the ecliptic, Atlas would pass about 28.96 million kilometers from Mars in early October, then swing within 97.15 million of Venus 4 weeks later, and finally skim 53.7 million from Jupiter the following March. These are not grazes in a planetary defense sense, but for an interstellar object, they form choreography. Most such visitors miss everything by hundreds of millions of kilometers, if they ever come near the plane at all. The analysts let every variable float across many runs, from velocity and inclination to small non-gravitational terms. The same pattern kept reappearing. It was possible to smudge a date by a few days or move a distance by a small fraction, but the chain of 3 notable passes persisted across the cloud of results. Quantum AI reframed the question. Instead of asking how unlikely a single thread might be, it examined the entire woven fabric of possible threads and ranked which fabrics survived the observations. The fabric that included the 3-planet survey pattern remained thick while others thinned. This did not prove intent, but it crushed the claim that chance alone explains the geometry. The lab stopped short of bold labels, yet the language shifted. Guidance became the working term. Guidance does not require an organism, a pilot, or even an awake machine. It only requires some coupling between what Atlas sheds and where Atlas goes, and that coupling appeared in the data. Add the near-ecliptic entry, the disciplined emission cadence, and the nickel skew, and the probability cloud narrowed further. Dissent remained healthy. One group argued that our surveys are biased toward objects that cross the plane where we look most. They were right, and the models included that bias, which is why the ranking mattered. Another group argued that resonant gravitational structures in the galaxy might funnel bodies into preferred orientations. That too made the input list, and was not strong enough to save a purely natural picture. The most uncomfortable feature was temporal. In a span shorter than a decade, humanity detected 3 interstellar objects after a history of none. A burst explained partly by better eyes, and partly perhaps by the fact that the sky is busy in ways we are only now able to notice. If the busyness includes surveys that are not ours, what are the surveyors measuring, and how many passes did we fail to see before we built instruments that could count them? If guidance holds, what does the sequence reveal about our blind spots, and whose clock could be setting time? Vulnerability, planetary defense, and the limits of comfort. Planetary defense is a set of habits more than a wall. We scan the sky, fit orbits, and assign risk scores while we develop defenses. The habits are improving, yet the gaps remain large. In 2013, a 20-meter object arrived over Chelyabinsk from a blind direction and detonated with energy equivalent to hundreds of kilotons, injuring thousands and shattering windows across a city. No warning reached the people below because the body came from near the sun on a shallow path and evaded both surveys and military radars. That lesson is never far from the screen when analysts talk about Atlas. This visitor is kilometers across and was found only because a dedicated network caught a faint motion against a crowded field. If there had been a collision course rather than a survey course, the interval from confident detection to consequence would have been short.
It's possible that such an event could happen again. This was actually the largest fireball that we've seen in a long time, since about 1908.
Quantum ranking does not make that problem gentler. If some interstellar bodies can alter their path by trimming momentum through timed shedding, the assumption that nature will not aim becomes weaker. It does not matter whether the guidance is ancient, simple, or purposeful. The practical risk is the same because any object that can adjust late makes the window for reaction small. Agencies can answer with better cadence, more all-sky coverage from multiple longitudes, dedicated space-based telescopes that watch from angles the ground cannot see, and faster pipelines from detection to characterization. They can run tabletop exercises that assume an object is adjusting and measure how plans hold when predictions change. None of that guarantees safety, but it sharpens reflexes before reflexes are needed. On the technical side, the Atlas case refreshed interest in missions that can intercept, sample, and image future interstellar visitors. A flyby bus with an autonomous camera, a dust analyzer, a spectrometer, and a transponder can answer in hours what months of remote inference struggle to settle. Even a single image that resolves structure or a mass spectrum that shows engineered isotopic ratios would collapse the probability cloud from debate to decision. Objects like Atlas do not loiter, and interstellar velocities punish slow launch cycles. That is why some teams argue for a standing interceptor kept fueled and sleeping at a parking orbit, ready to sprint after the next alert. Whatever path prevails, the ethics will need as much care as the engineering. If a visitor is guided, do we approach quietly or announce ourselves? And who speaks for many nations at once? Those questions sound speculative until a simulation narrows probability and a new track crosses the newsfeed. Preparedness here is not a mood. It is a plan we either write before we need it or write while the sky is already moving. What practice closes the next gap? Meaning, perspective, and the story we tell ourselves after the numbers. Every few generations, an observation forces a culture to redraw its mental map. A sun-centered cosmos replaced an Earth-centered one. Moons around Jupiter toppled tidy hierarchies. Photographs from the lunar surface reframed a planet as a globe suspended in darkness. None of those moments made the sky hostile, yet each stripped away a layer of comforting illusion. The Atlas simulation sits in that lineage because it makes a familiar faith wobble. The faith that the solar system is a quiet neighborhood unless chance rolls a bad number. Even if the guidance signature fades, the exercise has taught a humbler lesson. We cannot assume ignorance across the sky simply because our tools were too weak to notice visitors before. The acceleration in detections is partly better hardware and partly a reminder that deep time is busy, and we only recently learned to listen. That realization carries both dread and opportunity. Dread because awareness widens the space of risk. Opportunity because awareness also widens the space of choice. Quantum modeling did not conjure ghosts. It mapped which explanations deserve more of our attention, and that map points to specific actions we can take without committing to extraordinary claims. We can build an interceptor that does not sleep through the next pass. We can place infrared eyes where sunlight never blinds them. We can share alerts as readily as we share weather, and we can write an agreed protocol for first approach that treats the unknown with respect and caution rather than bravado. Those steps are not an admission that Atlas is a craft. They are an admission that humility is cheaper than regret. A separate thread runs through the data like a whisper we half remember. If the pulses are more than geology and ice, if the nickel skew is more than a quirk, if the 3-planet survey is more than luck, then somebody else once learned to ride momentum with gas and dust. That does not make them gods, invaders, or saints. It would make them engineers who understood the same physics we study and solved a navigation problem in a style that leaves a signature we can read. If that is the story, the emotion it asks of us is not fear. It is curiosity, discipline, and a willingness to be students of a sky that might contain neighbors. Neighbors need not be close, recent, or even alive. They can be far, old, and silent, yet still teach through relics and habits. Atlas might be such a teacher, even if the lesson is only that probability can carry messages, when language cannot. The next object will come, and a simulation will run, and again we will weigh humility against certainty. Which would you rather carry into that future? A plan sharpened by practice, or a story that collapses the first time the numbers refuse to flatter us? If 3i Atlas proves mundane, the discipline it forced on our tools and our thinking will have been worth the effort. If it proves guided, then we met that fact with eyes and a plan rather than panic. Either way, the lesson is the same. Pay attention, compare possibilities, and prepare to act faster than comfort allows. Subscribe if you want the next chapter as soon as the data moves. Share this with a friend who still thinks the sky is quiet, and tell me what you would build first. A ready interceptor, a deep space infrared sentry, or a protocol for first contact written by scientists, diplomats, and philosophers in the same room. The universe is speaking in trajectories and spectra. Let us listen well enough that the next time a visitor writes in that language, we answer in kind with clarity and the courage to learn.